Let's have a look at the last video. This one might be slightly longer. We're going to tackle three reasonably big questions. The first one not as big. In the diagram below, the circle with center O passes through the points C, D, and E, right? So we know C, D, and E all lie on the edge of the circle. We know that O is the center of the circle, which means that we have radii in all three of those, which means we have an isosceles triangle. Then OT bisects chord CD. So here we go with this one again. OT bisects chord CD. So line from center to midpoint of chord is also perpendicular to the chord. All right, obviously we have to prove that perpendicular, we have to state it, but we now know it's a fact. Okay, then all they've given us is angle DOE is equal to 4x. And then they come in with an absolute curveball here and tell us to prove with reasons that sine x times cos x is equal to OT over CE. So this will feel quite random because we've got some trigonometry mixed in with a proportion of some sort. That's what it feels like. Okay, so this would be like your last trig question, or maybe your first or last Euclidean geometry question. Okay, so what do we know? We definitely know that we have these right angles. So angle CTO and DTO are 90 degrees, line from center to midpoint of chord. Okay. Then we also know that OC is equal to OD, and that's because of radii. We know that angle C plus angle D together, they are 4x because the exterior angle of a triangle is equal to the sum of the two interior opposite angles. So therefore, angle C and angle D are each 2x. Okay, why is that important? Well, because this sine x cos x makes me think of the sine double angle formula without the 2 in front. So now I'm thinking, perhaps if I have a right angle triangle, I can actually move into trigonometry. And if I were to use sine of 2x, I could say that is opposite over hypotenuse, which gives me OC. It's got an OT and an OC, and I want a CE. So OC and CE are related in some way. So I'm now going to say sine 2x is equal to OT over OC. Don't have to give a reason for that. That's trig. Therefore, 2 sine x cos x is equal to OT over OC. Right, I'm still feeling quite happy with that. But now I don't want the 2 because they didn't have a 2. So I'm going to divide both sides by 2. And now I've got 2 OC. Here's OC. Can you see that double OC would give me CE, which is exactly what I'm looking for. So 2OC is equal to CE. So sine x times cos x is equal to OT over CE because diameter equals 2 times radius. All right, so a lovely combination question there with a bit of Euclidean geometry and then some trigonometry thrown in just to see if you are up to speed with your trig as well. Right, that was question 6. Question 7 looks more complicated than it is. We've got 2 circles touching internally at point M, and MK is now a common tangent to those 2. So because it's a common tangent, we can have tan chord theorem in the small circle, and we can have tan chord theorem in the large circle. A, E, and C are also points on the larger circle. So now we have M, A, E, and C on the larger circle, which means we have a cyclic quad, even though A and E aren't joined. So it does mean that I can have angles in same segment on the larger circle. B and D are points on the smaller circle. So on the small circle, I've got M and B and D. Chord CA is produced. Chord CA is produced to meet the tangent. So that means I have an exterior angle as well if I need it. It's a straight line. Triangle MEC is drawn, CA and EM, so those are now obviously straight lines, they meet at B. KB is a tangent to the smaller circle. So KB is a tangent to the smaller circle, but KM is also a tangent to the smaller circle as well as the bigger circle. D is a point on CM, and then AM and BD are drawn. Right, they give us KMB is equal to X, and they want us to work out 4 other angles, all equal to X. Okay, so let's have a look. I can definitely say tangent and chord BM on the little circle would take me to D1. So D1 is equal to X because of the tan chord theorem. Then if I take EM, that is a chord on the big circle. So tangent to chord, and so angles C1 and 2 are both equal to X because of the tan chord theorem in the larger circle. All right, then because KM and KB are tangents from a common point, we can say that KM is equal to KB, and therefore angle B1 is equal to X, angles opposite equal sides. And then if B1 is equal to X, I can also say B4 is equal to X because of vertically opposite angles. So there I have 4 different angles, each equal to X for various reasons. I'm not going to write those all down now. That will waste your time, but we have worked our way through all of them. All right, so now for an easy 2 marks, they want us to prove that BD is parallel to EC. So you've proved that D1 is X, you've proved that this whole angle ECD is X, but these happen to be corresponding angles, and therefore the 2 lines have to be parallel. Okay, so all I would say here is I would say D1 is equal to ECD, and that's already proved or proven. Therefore, BD is parallel to EC because the corresponding angles are equal. Right, so I now have parallel lines as well. Prove that angle A2 is equal to angle B2. Okay, there sits A2, there sits B2, and it's for 3 marks. Okay, so I think I want to find a missing link. So much earlier we said A2 is equal to E. So A2 is equal to E because of angles in the same segment, but B2 is equal to E because of corresponding angles, and therefore A2 and B2 must be equal to each other. Okay, so starting with A2 is equal to E because of angles in same segment. But then we said that B2 is also equal to E because of corresponding angles. Don't forget to name your parallel lines. And conclusion, therefore, is A2 must equal B2. It's classic logic there. They're both equal to E, therefore they're equal to each other. Right, and the last 2 marks, they want us to prove that ME times MD, ME, MD equals MC times MB. Notice everything is centered on this triangle. Okay, so we could prove similar triangles if we really wanted to, but I'm going to take a chance and say that this is proportionality. So within this pink triangle, because of those parallel lines, I can say that MB over ME is the same as MD over MC, and that's proportionality theorem, or line parallel to one side of triangle MEC. So if I cross multiply, ME times MD is the same as MC times MB. Right, so that actually was a very nice, mostly level 2 kind of geometry question. Lots of grade 11 geometry and a little bit of grade 12. Okay, so let's see if we can finish off with a bit of a challenge over here. Question 8. Lots going on in this question. We have a cyclic quadrilateral. So if I have a cyclic quad, I'm going to highlight it straight away. Chord SR produced. There's that magic word produced. It means a straight line, which means automatically R2 is the exterior angle of the cyclic quad, and P2 is the interior opposite angle. And chord PQ is produced. So here we go again. Exterior angle equals the interior opposite angle. KPL is a tangent, so anything tan chord. U and V are points on PS and PQ respectively, so that we have parallel lines. So our tangent is parallel to UV, which is parallel to SQ. And then lastly, they've told us that angle P1 is equal to X. So this time they want 5 other angles equal to X. So I'm going to go tan chord, is equal to the angle in the alternate segment. Then I can go parallel lines, takes me to V1 is equal to X, corresponding angles. I can also use alternate angles, which will take me to that one. Angle P3 is equal to V1, and angle X1 is equal to U1. And angle, sorry, not X1, P1. P1 is also equal to S1 because of alternate angles. So 1, 2, 3, 4, 5 angles all equal to X, and those are very easy, generous marks. Now they want me to prove that PQ is equal to PS. It's only for 1 mark, so it isn't even really a proof, it's just explain why. So PQ is equal to PS because Q1 is equal to S1, and therefore its sides opposite equal angles. So PQ is equal to PS because of sides opposite equal angles. Also for 1 mark, prove that KP is a tangent to the circle going through P and U and V. So if there was a circle here, prove that KP is the tangent. Well, that's okay because we've got the angle between KP and PU, that's angle P1, is equal to angle V1. That's already proved. Therefore, it must be a tangent because it's the converse of the tan chord theorem. So all I'm going to say is angle P1 is equal to V1, already proved. Therefore, KP is a tangent, etc., because of converse tan chord theorem. Sorry, that's not on the screen. Okay. Now, give a reason why PU over PS is the same as PV over PQ. That is absolutely classic proportionality theorem. So our reason there is simply line parallel one side of triangle. All right, so those little 1 mark questions are there just to alert you to certain properties in this particular question. Now we must prove that triangle PTS is similar to RTQ. Let's have a look at that. PTS, so the big triangle, is similar to RTQ, this little one. Okay. So because they've given me the order, I'm going to follow their order and I'm going to say, why is angle P, which will be P2, equal to angle R, which is R2? So why is P2 equal to R2? Exterior angle of cyclic quad. Why is T equal to T? Fantastic, common angle. And therefore, without much fuss, angle S, which is the whole of S, S1 and 2, is equal to Q3. Okay, well, third angle of triangle or exterior angle of cyclic quad again. So a really lovely similarity proof. I'm going to just put it up for you instead of taking the time now to write it all out. So there are the two triangles that we're trying to prove similar. Angle T is common. P2 and R2, exterior angle of cyclic quad. Third angles. Therefore, the two triangles are indeed similar. Right, so we're gathering lots of marks in this question. For 2 whole marks, prove PT, so I'm looking above, times RQ equals PS times RT. Yes, okay, that's perfect. I don't have to do anything special. I'm using my similar triangles and I'm using the frog face, if you want to call it that. Thank you to the Mind Action Series textbook authors there. So PT divided by RT is equal to PS over RQ, and that was similar triangles. And now if I cross multiply, I've got exactly what I'm supposed to have. Done. Okay, now for the last question, which can be quite an interesting one to tackle. There's lots of ways around it, so we've just got to find a way where the logic flows quite nicely. What's scary about this one is this big square root, and then we're subtracting over here. So what I tried to do is I tried to reinterpret it for myself and said, if I didn't have the square root sign, then what I am required to prove is PQ squared equals PS times PT minus TS times RQ. So it was that PQ squared that then got me thinking it must be something to do with the similar triangles again. So I've just got all of my proportions from my similar triangles that I proved in A, and now I'm trying to match up to see which ones seem to match the best. So PS RQ TS. So the only one that doesn't come into it is PT. So I'm feeling reasonably comfortable with the fact that I'm going to use those two. Okay, so again, this is because of similar triangles. So I'm going to say PS times TQ is equal to TS times RQ. Okay, so what are my problems over here? Well, the TS times RQ is just not a problem. The PS and the TQ are a bit of a problem, but PS, sorry, back to my sketch for a minute. PS I proved equal to PQ. So I can say PQ times TQ equals TS times RQ. Why? Because PS equals PQ. So the one that's giving me a headache is actually TQ or QT. What do I want instead? I want PT. So let's have a look at QT and PT. There's QT, there's PT. Would you agree that QT is just PT minus PQ? Okay, I'll say that again. QT is PT minus PQ. So that's what I'm going to do here. I'm going to say instead of QT, I'm going to make it PT minus PQ. And now a little bit of algebra, PQ times PT minus PQ times PQ equals TS times RQ. And now I'm feeling particularly proud of myself because that's PQ squared. So I'm going to put the PQ squared that side, PQ times PT minus TS times RQ. Hooray! So the only thing that's not right is I've got a PQ and I want a PS. So I can just change it back again. PS times PT, TS times RQ is indeed equal to PQ squared. Okay, so it was a little bit of a runaround for 4 marks, but quite a clever question to work with. I suppose I should finish by saying, therefore, PQ is the square root of PS times PT minus TS times RQ. If you've done this one a few times, it's very hard to forget that you've seen it. Then it's just to get that reasoning back again. Okay, so I hope that that gives you a lovely overview of the different kinds of Euclidean geometry questions that you can be asked in grade 12, particularly where you're combining grade 11 and grade 12 knowledge to answer these questions. There are plenty more. I've just picked out some of the interesting ones. So go back to old papers and have a look for some more.